Hey everyone, so welcome to Amour Learning. Let me just make sure everything is set up for this YouTube live session as I'm kind of running pretty much everything over here. I'll increase the music just a little tiny bit. So at least a little bit, you can hear it a little bit. All right, so we have a lot to say. So first off, we have officially launched our statistics course. So if you have not done so already, make sure you check out the statistics course. So you're gonna get a feel for how professional studio quality videos these are. These are not just like videos that were filmed in some sort of basement. These are actually like really good lectures. So check out those videos if you haven't done so. Also, make sure that you subscribe to our YouTube channel. We have really gotten a huge movement of subscribers. So a couple months ago, we only had like 20 subscribers, and now we're at 200. So we've already multiplied by 10 in a matter of a few months. And it's looking like we're gonna be able to reach our 1,000 mark by the end of this year, which would be really exciting. So again, if you haven't done so already, please subscribe, support this channel. This is Amour Learning. Let me tell you a little bit about what we do. We provide free videos for everyone, and these videos are professional studio quality math lectures, so that they're not super engaging yet. I haven't gotten to that part, but they are very much lecture style format. So we are actually going to be transitioning to a new style where I actually interview students. So if you've ever seen a channel like Veritasium Veritasium. I was gonna say Vitsauce, but he doesn't really interview people. Veritasium, Derek will go out and he'll just like interview people, and I actually started doing that, and I asked questions like, what is slope? Why did your teachers switch from y equals, they went all of a sudden to f of x equals? What was that all about? What is an angle? Just these questions that are very, very central to both math ed research and just high school mathematics. And I make the argument that high school math is taught in a way that's very procedural, very memorized based, and it's part of the reason why students struggle in classes like calculus. And this is some stuff that a lot of researchers like Pat Thompson and Cameron Barley, I can't say her last name, they've been working a lot on this sort of thing. There's a lot of researchers out there that are working on this sort of thing. So, and by a lot, I mean not a lot. So I'm really excited to be able to kind of exploit this research in video format so you guys can actually see what these students are saying. Now, about that, we had originally planned on releasing one lecture per day, but we have some pretty cool news. The news is that we are producing 3 videos every single day. So if you check out our channel, you're gonna see new content every single day. And on Thursdays and Fridays, we offer free tutoring to anyone who needs it. So that's what's going on right now. This is the free tutoring session. So if you have any math questions, please ask over here. We had a question last week about Markov chains, and we're gonna actually get into that today. I'm gonna be writing down some Markov chains, and you're gonna see in this little general area right here, you're gonna see some math regarding Markov chains. That's gonna be pretty cool. So yeah, that's basically it. Again, just a recap of the news. We have new course coming out, 3 lectures a day, plus YouTube Live every Thursday and Sunday, all professional studio quality, done professional video editing, green screens, you name it, it looks really, really good. So check out those new videos. They're coming out every single day. By the way, if you're wondering when they come out around noon, somewhere between noon to 3 p.m. Around Central Time. and maybe a little bit later in the evening for Eastern Standard Time. So check that out. Now, I want to get into this tutoring session. So again, if you guys have any math questions, please post your math questions over here in the live chat, and I will respond to every single one of you. So we're going to go over quickly to, I'm going to pull up my whiteboard for you guys so that you guys can see it. It's going to be a little weird because I have a program and I'm kind of running this on my own, but it's whatever. You guys see all this fancy stuff. This is what I'm working with literally right now. It's pretty insane, pretty intense stuff. But I just want to go over Markov chains because that was a request that I got from one of my subscribers. So let's talk about Markov chains. Now, when you think about chains in general, I think about like a picture like this. Markov chains are very different from these kind of chains. These are not Markov chains. First off, what a Markov chain. We've kind of already talked about this in one of the live sessions, but I'm going to reiterate because now we actually have better internet access. You guys will be able to see. Hopefully this stuff will be pretty live. You'll be able to see it very clearly without any lag or delay. And so here we go. This is the idea. If you're working in computer engineering or any sort of engineering, you might have a machine that changes to different states. So we have, let's say, 3 different states. 1, 2, 3. So let me see if I have my calculator anywhere. I don't. I'm gonna have to grab that in a moment here. But here's the idea. You have these 3 states, and you have some arrows drawn. This is basically more or less a graph. And by graph, I mean graphs from graph theory. So you have arrows drawn every which way. So let's try to get this. It doesn't matter where you draw them, so long as you just draw them. That's the whole idea of graphs. You have arrows going out and inside itself, and I'm going to explain what these are. So the idea is you have different states. Maybe, for example, you have a gas pump. And this is like the default state where it's, nothing's really happening. I'll use a different color real quick. Here you have nothing really is happening over here. But 2 is when someone like puts in their credit card and you have this new state. And then here is the actual pumping gasoline state. So you have these different states that a machine might be in. And the idea with Markov chains is that you're trying to figure out what might happen in a system where you can change states randomly. So, and this is more for chaotic systems. So you have like a system, in this case, you have 3 states, but you don't really know exactly which state you're changing from in the future. You just know the probability of changing from one state to another. So let's give an example. Let's suppose that it's impossible to go from state 1 to 3. So I'm going to put zeros here. And what these zeros represent is that the probability that a state changes from 1 to 3 is zero probability. And to go from 3 to 1, it's also 0 probability. So that's just saying basically there's no way that the state can go from 1 to 3 or 3 to 1. Well, let's also say like the probability from that 1 stays where it's at, the probability that 1 goes to 1, let's say is like 30%. Let's say the probability that 2 does not change is like 40%. And the probability that 3 doesn't change is like 50%. Now, I'm going to real quickly take a look at the state 1. Now, when you're at state 1, you have 3 different options. You can stay at state 1, you can go to state 2, or you can go to state 3. But those are your only 3 options, meaning that the total probability should add up to 1. Well, all the arrows that are sticking out from 1, let me use a different color here. All the arrows that are sticking out from 1 are basically what the arrows that are sticking out of 1 are the different ways that state 1 can change. So state 1 can go to state 3, state 1 can go to state 2, or state 1 can stay by itself. So those are all the 3 different options. And so that, therefore, the total probability should add up to 1. So the probability that going from 1 to 3 is 0, 1 to 1 is 0.3. Therefore, the probability of going from 1 to 2 is what's left over, which is 70%. If the probability from going to 2 to 1 was 10%, then the probability of going from 2 to 3 would have to be 50%. And let me explain why. Because the probability from 2 going to itself is 40%. The probability of 2 going to 1 is 10%. So the probability from 2 going to 3, that's the last option, has to be what's left over, which is 50%. And now the probability that 3 goes to itself is 50%. The probability that 3 goes to 1 is 0%. Therefore, the probability that 3 goes to 2 is also 50%, the leftover 50%. Now I'm going to change the color real quick back to blue so that you guys can see this a little bit better. And then we're going to take a quick break, and I'm going to actually grab my calculator. So let's see here. This was 0.7. This was 0.5. This was 0.1. This was 0.5. And I believe that's it. All right, we're going to take a quick break. I'm going to go grab my computer, and then we will discuss what these Markov chains can do. Now, in the meantime, while I take this quick break to grab the calculator, make sure you post your questions in the live chat so that you can ask all of your questions. So we will take a quick break. Be right back, guys. All right, we're back. We are back. Let me. So now I have my calculator. This would have been a little bit more convenient to have, but sorry about that, guys. That's okay though. So let's get back to these Markov chains. All right, so this is what you see. You see a Markov chain right here. Now this is a pretty complicated scenario, and with a Markov chain, you might ask a question like, if we start here at state 1. So I have this ball right here, state 1, and well, I'll use a star. Star represents I'm at state 1. Now this star might stay at state 1, it might move to state 2, it might move to state, well actually it probably won't move to state 3 because the probability of moving to state 3 is 0%, so it definitely won't go there. So it'll either stay at 1 or it'll go to 2. But, so I know what could happen in the next instance, like in the next movement. So if after one change of state, I can probably predict where it's going to be. There's a 30% chance that it's here and a 70% chance that it's here, simply because the probability of moving from 1 to 1 is 30% and the probability of moving 1 to 2 is 70%. Now what becomes complicated is where am I going to be after 2 changes of state? So if I'm here, I could stay here, and then I could go to 2, or I could stay here and stay at 1, or I can go to 1, then move to 2, then move to 3. So it's important to understand that there are 3 options. I can be at state 1, I could be at state 2, or I could be at state 3. So the question is, where am I going to end up here? And that's where Markov chains allow us to, well, actually linear algebra allows us to solve this problem. So here we have our Markov chain, but I'm actually going to create a matrix. And if you don't know what a matrix is, then this is about the part where I might lose some students. So here we have state 1, state 2, and state 3. And I'm going to create a matrix. And on top here, I'm also going to write 1, 2, 3. Now the probability of moving, so what I'm going to do is I'm going to take this entire thing right here, and I'm going to shove it into this matrix that I'm drawing right here. And so the probability of going from one, by the way, this is where we start, and this is where we stop. So this is stop. So in this case, the probability from going that where you start at 1 and you end at 1 is 30%. So that we would write 0.3 right here. And let's use a different color other than red, because red might be a little bit off-putting. So I'll put a 0.3 here because the probability going from 1 to 1 is 0.3. The probability of going from 1 to 2, let's see what that is. That's this one right here, is 0.7. So we're going to put a 0.7 here. Probability of going from 1 to 3 is literally 0. So notice right off the bat, these three numbers need to add up to 1, as we mentioned earlier. Probability of going from 2 to 1, let's see where that is. That's this right here, is 0.1. Probability of going 2 to 2 is right here, which is 0.4. And the probability of going from 2 to 3 is right here, which is 0.5. And then the probability of going from 3 to 1 is 0. The probability of going from 3 to 2 is 50%. And the probability of going from 3 to 3 is also 50%. So notice that the rows add up to a total probability of 1. So 0.3 plus 0.7 is 1, 0.1 plus 0.4 plus 0.5 is 1, 0 plus 0.5 plus 0.5 is also 1. Now, we can actually use this matrix. This matrix is going to be really important. We're going to call it, we're going to give it a variable. We're going to call it A. Oh, we'll call it T, because it's our like transition matrix. Now, if we wanted to find what the probability of starting at 1 and ending at 3 after 2 moves, to figure that out, we could use this matrix to help us. And the way we would do that is we would take our matrix T, and I'm going to use a different color here. Let's take T, and we're going to raise it to the nth power, where n represents the amount of transitions we need to go through here. In this case, we're going to use 2 transitions. So we're going to multiply T by itself. And I'm going to explain why this works in a moment here. So we're going to figure out what T squared is. I'm actually going to write what T squared is over here. At least I'm going to try. All right, so I need to multiply this matrix by itself, which is why I have a calculator here. So I'm going to go into my calculator, and I'm going to enter in this matrix that I have over here, and then I'm going to multiply it by itself. So let's input this matrix in this calculator. So 0.3, 0.7, 0, 0.1, 0.4, 0.5, 0, 0.5, 0.5. And then I'm going to multiply that matrix by itself. And this is the probabilities that I get. 0.16, 0.49, and I'm going to need some more room here. So let me give myself some more room. Let's see here. 0.16, 0.49, and 0.35. And then 0.07, 0.48, and 0.45. And then that doesn't look like a 5. Let's try that again. Ooh, there we go. And then 0.05, 0.45, and 0.5. Alrighty, so let's talk about what these 9 numbers represent. Again, we have specific locations on our matrix. Specifically, I'm going to put 1, 2, 3 over here, and 1, 2, and 3 over here. Now this is t squared. We're talking about t squared right now, meaning that we're finding the probability that you start at 1 and end at 2, for example, after 2 moves. So how can we start at 1 and end up at 2? Well, you can start at 1. Here, let me delete a couple things here so we don't distract ourselves. So we could start at 1, stay at 1, and then move to 2. Or we can start at 1, move to 2, and then stay by itself. So those are the 2 options. And we need to add those probabilities together, and that's how we get this 0.16. But we're going to see why that works if we take t and multiply it by itself, because it's pretty cool how that math works. Now, so we have 0.16 represents that the probability that you start at 1 and you end up at 1 is 16%. Excuse me, hold on 1 second. Excuse me. Okay. Now, now this actually works for any n transitions. So right now this is 2 transitions. But let's see what happens after 5 transitions. So let's see where I'm at after 5 transitions. So I'm going to take my matrix and I'm going to raise it to the 5th power. And again, I want to explain why this works. So this is what I get. I'm going to actually write it over here. T to the 5th power is, it's going to be kind of hard to read, 0.0, here, let's give some more room, 0.07, and I'm rounding to 2 decimal places, 0.47 and 0.46. And then it's actually 0.47 pretty much all the way down over here. So 0.47, 0.47. And then over here is 0.47. Over here is 0.47. And then over here is 0.07. And 0.07. Now I'm rounding, so just keep in mind that the total probabilities of these rows is not 1. We can actually kind of see that there is this tendency towards what's happening at the final end result. So I'm going to write these numbers. The probability of going from 1 to 1 looks like 7%. The probability of going 1 to 2 is 47%. The probability of going from 1 to 3 is 46%. And this is after 5 transitions. Keep that in mind. This is actually really surprising. If you notice, these rows are basically more or less the same. Well, actually, sorry, the columns are more or less the same. Well, I should say, no, I'm sorry. The rows are more or less the same. What that means is, no matter where you begin, it actually doesn't matter. The starting position does not matter. It looks like there's a 7% chance that I'm going to land at 1, about a 47% chance that I'm going to land at 2, and a 47% chance that I'm going to land at 3. But what I'm going to do is I'm going to actually figure out what is the limit as n approaches infinity of t to the nth power. So I'm going to look at what's going on with my transition matrix over a very large portion of transitions. And this matrix is actually rather interesting because you would assume that you would be in random positions on your there's state 1, state 2, and state 3. You'd assume it'd be 33% because it's totally random, right? Well, it's not. It's actually not because of how the Markov chain is, I guess. So what I'm going to do is, to figure out what t to the nth power is, I'm going to take my matrix and I'm going to raise it to a really big number, like 100. And I'm getting that this number is 0.07, 0.47, and 0.47. And that doesn't, I don't believe that adds up to 100%. I think that goes a little bit over, but that's because I'm rounding. So this is actually the same thing all the way down. Exactly, and that's exactly kind of what we would predict, that after a certain number of transitions, it doesn't matter where you started from because you're going to be moving randomly, but then after a while, you can kind of see how the Markov chain looks, where you're probably going to end up. It's really hard to go back to 1. It's probably you're going to be somewhere between 2 and 3. Now let's talk about why this works. So if we have our matrix, our Markov chain, which was, let me see if I can pull it up on my calculator because I just deleted it. So it was, this is T, 0.3, 0.7, and 0. And then 0.1, 0.4, and 0.5. And then 0, 0.5, and 0.5. All right, so let's talk about what t squared actually is. So what is t squared? Well, t squared is t times t, but let's just talk about a random position. Let's start with the first position. How do I get that number? Well, it's the first row times the dot product between the first row and the first column. So let's look at what that actually is. So t squared sub 1 comma 1 is the dot product between the vector 0.3, 0.7, 0, and the vector 0.3, 0.1, and 0. So it's the dot product. And to get the dot product, we have to, I believe, we have to multiply in line with the two vectors. So we multiply 0.3 by 0.3, 0.7 by 0.1, and 0 by 0. And we have to multiply all of those and then add them all up, I believe. Yes. So it's 0.3 times 0.3 plus 0.7 times 0.1 plus 0 times 0. And that is where we get, I believe it was 0.16. And let me double check that. 0.3 times 0.3 plus 0.7 times 0.1 is 0.16. Now, why does that work? Why is it 0.6? Well, let me go back to, we're going to remember this, by the way. This is extremely important, this portion right here. We're multiplying 0.3 by 0.3, 0.7 by 0.1, and 0 by 0. Now, let's talk about how can you start from state 1 and end up at state 1 after 2 transitions. Well, you can stay at state 1 and then stay at state 1 again. You can move to state 2 and then back to state 1, or you can move to state 3 and move back to state 1. And that's actually exactly what we see right here. And this is kind of the interesting part. This right here is the probability, oops, let me fix that, there we go. This right here is the probability that we stay at position 1 twice. This right here is the probability that we move to position 2 and then move back to position 1. And this is the probability of me moving to position 3 and then moving back to position 1. And those are the 3 options. Now, there are many different options that could have happened. I could have moved from position 1 to position 2 and then from position 2 to position 3. But all I really care about is looking at the scenario where I start and end at position 1, which is exactly what this is right here by definition. And that's why we're doing this. So it looks like it works from a theoretical standpoint. This is like a more semi-conceptual understanding of Markov chains. Anyways, I'm going to see if we have anybody who's willing to, well, not willing to, who wants to ask any math questions. So again, if you haven't done so already, check out or post your live chat or your math questions in the live chat. So let's see if we have any math questions so far. It looks like we don't. So I'll give you guys a little bit of an outro here. Stay tuned. Again, we are releasing many new videos regarding statistics. So our first course is going to be on statistics. The second, I have the hiccup, sorry. The second course that we will be releasing is basic math. So that one's going to be coming out in a few months. That one I'm really excited about because for those of you who had trouble in math in your high school days or your middle school days, well, a lot of that's going to be explained with both research and evidence in our basic math course. So stay tuned for that. But for now, we are just pumping out videos for our linear algebra course. So please check those videos out. They're free resources. You can learn a lot about statistics, like what's an independent variable or dependent variable. We talk about statistics versus parameters, like what is statistics. These are really important questions that I think everyone needs a good concrete understanding of. Anyways, just real quick, if you haven't done so already, subscribe to our YouTube channel. Check out our website at amourlearning.org, where we have some of these courses. We're posting some of these videos up on that website. And thank you guys so much for your support and everything that you guys are doing to help us. So my wife and I really appreciate our subscribers, our fan base. So we just hope that this free resource can reach out to many people. If you haven't done so already, share this resource with someone. Tell someone, hey, you're struggling with math. I know a resource every Thursday and Sunday at 9 p.m. Eastern time where you can get some free math tutoring. So check that out. That's going to be really good help for just a friend of yours, because there are high school students that you probably know, and chances are they're probably struggling in math. Thank you guys so much, and I'll see you on Sunday at 9 p.m. Eastern time. Thanks, guys.